Can you see the screen? All right. So some of you have attempted this question, and I have made a note of all of them. And so those who could not attempt, who could not write to me with the answer of this question. So last time we left the session with a question that if you have a plain text file of all the Lord of the Rings books, and how would you find the frequencies? Okay. So is anybody has any more answers? Does anybody has any more answers? Because some of you have replied in the email. Those are very good answers. Yeah. A very small brief approach will also do, not necessarily coding one, but any tools will do. All right. So yeah. So this is the general approach which most of you have already sent me. There so create a frequency table. Frequency table is like a dictionary which has word and the meaning. Word means key and the meaning is value. So similar to dictionary, you have a hash table in almost every programming language. All right. So is my voice low for everyone, or is it something wrong with only Kalyan's audio? Okay. Okay. So probably Kalyan, you may need to increase the volume, or yes, correct, Anand. So we'll discuss that approach. All right. And so Kalyan's approach is if we have large amount of data, sorry, Anand's approach is that if we have large amount of data, we should read it in chunks into the buffer, then process the data in the buffer, then read another chunk of data into the buffer. Right, right. So the problem would be to combine all these buffers at the end of day because we need to compute the overall frequency in the whole data, not in the individual buffer. Correct, Anand? All right. So the general approach is that you create a hash table, which is like a dictionary, which has key and the values. The quality of a hash table is that the retrieval and addition is blazingly fast. Okay, it's very fast. The addition of a new key is really fast, as well as finding an existing key in the hash table is extremely fast. It's like array operation. In the array, you look up at the index, the zeroth index, first or second, and also you basically write to that index. So seeking a key is really fast in case of hash table. All right. Now, once you have created a hash table, go through the file, picking one word at a time and checking against the hash table. If that word exists in the hash table, increase the frequency. If it doesn't exist, add it. Add the word with the key. If it doesn't exist, then add the word as the key and value as 1, and keep on doing it until the whole file is finished. And once the file is finished, you print the result from the hash table. All right. Is this approach clear for everyone? So is there a word which you don't understand the meaning of? Like, so the objective is finding the frequency of unique words. Out of this word, what are the total number of unique words and how many times they have occurred in the text? So is there something which you did not understand in this approach? So I'm assuming that it's clear for everyone. Okay, so let me just go through the logic once more. So does everybody understand the meaning of a dictionary or a hash table? Okay, so a hash table is like a data structure in which you can find a key really fast. Just like in a dictionary, you can jump onto a particular page and find the word very quickly. And here the annotation of dictionary is even faster than that. Okay. Okay. So you go through one word at a time from the file. If this word is found in the hash table, we pick up the word from the file, check against the hash table if it exists or not. If it exists in the hash table, increase the frequency. If it doesn't exist, then add it into the hash table and add the frequency as 1. Okay, and keep on doing it for all the words until all words are finished. All right, basically you are maintaining the count in the hash table for each word. Okay, all right. So now the question arises, this approach sounds really brilliant. So because all of you who have written to me with your solutions, I've also responded with, do you see any problem? So do you see any problem with this approach? Anyone? Yes, correct. So Manish says that memory is a limitation in this kind of approach. Good. Yes. Srinivas says it takes too much time. That's also correct. And Surya says, how much data can you load into the RAM? So this hash table consumes a lot of memory. Generally, it is more than 2x times of the actual data you want to store. So if you have got 5 GB of RAM. If you got 5 GB of RAM, you cannot load more than 2.5 giga. Sorry, you cannot load more than 2.5 gigabytes of data into the hash table, right? So RAM is something we have not specified here, Surya. All right. So yes, you cannot process the data. Okay. All right. So Mohan's point is that why not use binary tree? Treat the problem just like having the AND nodes to load an entire dictionary into the tree with the nodes representing the words and their count, and thereby you are avoiding checking against the existing entry. That's correct. So even in the binary tree, before inserting a key, you will have to find out where is that particular node or does it exist or not. Correct? So for each insertion or updation, it will take log n times of log n order of complexity, and hence it is going to take more time than what we have here. Okay. And Vivek's question is that why does it take double the size? So this the hash table is a little bigger data structure. If you look into how the hash table is implemented, you will realize that it does take quite a much of memory. All right. And as you can guess that at least it will take the memory equal to the equal to the size of the input text. Correct? So we have got two values stored in the hash table. One is the word and other is a number, right? So that makes it close to 2x, along with other bells and whistles like the internals of data structure. Brilliant, brilliant. So Kalyan says that if the words can be sorted in an ascending order just by comparing the previous word and the current one, it can be achieved. Yes. So that is another approach. So another approach is that we basically order the words so that we don't have to load everything into memory. So sorting is a problem which has been there since which has been being solved for hundreds of years. And if you can convert this problem into sorting, as Kalyan is suggesting, then it will be really, really easy. Okay. Why? Because sorting can be done in a small memory. You can sort 100 terabyte of data using a smaller memory by reading chunks in the approach similar to the approach mentioned by Anand, that you pick up chunks of the data, try to sort it, then sort the sorted data, merge the sorted data. Okay. So basically that's the approach we are going to discuss further. All right. So is are things clear till the point that this approach is inefficient when it comes to the bigger data? Correct? Because here all we expect is all the data should be in the single hash table, and we should be able to load everything into a single hash table, right? This approach number one. So this frequency hash table, we expect that it should have all the words, only then it mean anything. Otherwise, it will not mean anything. Correct? Because if you try to imagine that one book per hash table, if you try to imagine that there is one book per hash table and we compute the, so that will only, will be only able to compute the frequency of each book separately. Now to combine all these frequencies is going to be a tougher task. Yes, Vivek? So Vivek's question is, if you are keeping the count, why we would have all the data? So in the worst case scenario where all the words are unique, okay, you'll have to have that kind of data, right? So we'll have to keep word and the counts both. And in case all the words are unique, that means it is going to be bigger than the input data. Correct? So is everybody comfortable with this? So Sabrish's question is, what is the time of hash table? Probably your question, Sabrish, is that what's the time of insertion and what's the time of addition? Correct? How much time does it take to insert? And so good part about hash table is the insertion time. Okay, so what is the limit? I read it, misread it, sorry. What is the limit of a hash table? So let me explain the time part first. Yeah, okay. So let me explain the time part first. So in the insertion and retrieval time in a hash table is fixed. It's irrespective of how many values we have in the hash table. All right, that makes it very suitable for most of the work. While in case of other data structures such as tree, it takes the time is proportional to the logarithm of total number of elements. So that's a little bit advanced topic. Now, Sabrish's question actually was that what is the limit of a hash table? So hash table is limited by how much memory do you have in a computer. If you have 100 GB, you can have a 100 GB size of a hash table. So it is limited by the hardware, correct? And then further points arises that how big is your key, how big are your values, and based on that. So as a general idea that you should get it. So in case of Java, the total memory taken by hash table is close to 2.5 times the actual input data. Okay. While in case of a Python, the total amount of memory taken by hash table is close to 4x, 4 times the actual data, your actual file. All right. Now, going ahead, and some of you had suggested this approach in last discussion, that the SQL approach, the database approach, and some of you also wrote in the email with this approach. Okay, so the approach was break the books into one word per line, meaning ha- have a big table where there is only a one column, and in each column per row you have one word. Okay, you have one column, and each row contains only one word out of this text. Okay, so you break down the whole text into one word per line and then insert it into the databases. Okay, and once you have done that, all you need to do is do a group by clause. Okay, select word and then comma, count star from the table and group by the word column. Okay, so is this approach okay with you? Yes? Other than Vivek, anybody else? Somebody says it sounds like heavy duty approach. That's partly correct. Yes. Query execution time. Yes, it is going to take some time. But it's still, Approach number two will not suffer from the memory limitations. Okay, because databases are correct, Mohan. Thank you. So Mohan says you will have to again sort for grouping. So we are not sorting the data while inserting the data into the database. We are letting the database sort for us. That's correct. And sorting is going to be heavy duty as usual. But the important part in this is that databases, almost all the databases, are heavily designed such that they can order any amount of data. So they will not try to load all of this data into the RAM and try to do the sorting. They will try to do all sorts of all sorts of algorithms in order to solve this. Okay, so sorting, they can sort a huge data, the data that goes beyond the memory. All right, good. Anybody else? So whenever we talk about computing an algorithm, so the most prominent algorithm is probably sorting algorithm. And sorting algorithm is something which is so widely used and so omnipresent that everybody tries to solve the sorting problem. And every year, still today, every year at least there are few enhancements in the sorting algorithms. All right. And whenever we talk about computing, we generally talk about sorting. Okay. Anybody? That's why I'm asking this question, which basically we started with counting the frequencies, but we ended up sorting the data. Okay. So most of the problems are like that. So anybody else here? Okay. Good. Now, see the next approach. Let me see who can understand this quickly. All right. So here, in this approach, we are using Unix command lines. In the Unix, we basically do things in a pipeline fashion. All right. Kalyan says it's a duplicate insert and performance issue in the previous one, probably this one you're talking about. All right. Yeah. So those are minor issues. Okay. Those are minor issues. And so when you say duplicate, where is the duplication of insert? You mean to say when group by does it, it internally creates temporary table, Kalyan? One is that we are inserting into the database table and then we are grouping it by. Other approach could have been when we're dealing with the database, we create an index on the column and as and when we are inserting the word, it's getting sorted. But that could have been a little more expensive. All right, never mind. So here we're going ahead. Now, in the third approach to solving the frequencies of words is you again you translate the each line into one word per line, meaning you replace space with new line. So the way here it is that you open the file, replace space with a new line, and hence you will get one word per line. Okay, so you can see the substitute slash t slash space and replace that with new line. And okay, So who doesn't understand Unix pipelines? If you don't understand, I can explain, no issues. All right, because that will also help us. Understanding this pipeline will also help us in future. What when we talk about something called Hadoop streaming. All right, so I've got three people. Anybody else who wants me to explain? So what does it mean by what does it mean? What does this means? All right, great. So I'll just take a little bit of time. Do not hurry, and let's try to focus on this. So whenever we execute a command like ls, it gives us the list of file. All right, or echo just echoes whatever we type. All right. So every command gives us some output, and it can take the input from the command line, or it can take the input from the user. All right, it can take the input from the user, like I say read x, so I can type here anything, so it has read the value. So every command can take input from two ways. One is from command line argument, other is from the user directly, and it can print the data to the screen. All right, so that's a command. Now let me open a text editor also, that will help us in. All right, so so we have each command. Okay, command has input and command gives output, correct? And input can be from command line argument, such as we said echo high. High is the command line argument. And standard input. Standard input is when you type. All right. Output is to the screen. Okay. So output could be from to the file and to elsewhere. Now the beautiful part of say Unix is started with when people figured out that there is a way we can make the commands communicate. Okay, so let's say that, and also there is a command called word count, to which you type things and it tells at the end of it how many lines were there and how many letters were there. So it's saying that 33 letters, 4 line, sorry, 3 line and 4 words. Okay, so for example, word count counts the word input to it. So right now when we executed the wc command, it took the input from the standard input and then counted the characters, word and lines and gave the result. All right, now to wc we input it from by typing from us. Now what if to wc we could send the input from any other command? Okay, for example, ls was giving us the list of files, it's coming to the screen. If we say pipe here and say wc, so whatever is the result of ls is going to wc. So ls, instead of giving this text to my screen, it will give this text to wc, and wc, instead of waiting for me to type anything, it will take the input from ls. All right, so this is called pipelining. Okay, so it told us that there are 116 lines in ls and 128 words, and this is the result. So we can say that from this input that there are 116 files in this folder. Okay, it just counted number of lines, number of characters, number of words for us. All right. So this is called pipelining. Pipelining helps us reduce a lot of hurdle, and pipelining helps us chaining various commands together in order to do a lot of automation. All right. Now, so this is called pipelining. Now let me take this example. What does this example do? All right. So in this example here, so there is first line. What does it mean? So first line means print the contents of my file. Okay. So let me show you this part. So is till now everybody is with me with respect to the chaining of the commands, the pipelining. So the to chain the commands, like here we did was here to chain the command, we said command one, then pipe, and then command two. Okay. Basically, it sends the output of command one to command two as input. Okay. So the output of command one becomes input to command two. All right. Now you will see the magic that you can do lot of cool stuff by combining these commands together. So here is one good example where we have basically chained four commands or pipelined four commands together. Okay, and I'll try to explain the meaning of each one. Okay, I'll try to explain the meaning of each file. Let's say I take a file called cat big. Let me just find a good file. So find is another command in Unix which can help us find file anywhere. So it found that there is a file big.txt. So let me make a directory of session 2. Move the file from big.downloads folder to current folder and say cat big.txt. Okay. Now if I do cat big.txt, it is going to scroll, it will read the data from big.txt and print it onto my screen. But if I pass it the output of big.txt to more will show one page at a time, like this. Okay, more will show one page at a time, like this. All right. Now this is my file. Okay. If and again, so in I mean I think I'll just take a small chunk. Let me just take a small chunk from this file. So cat small .txt contains these few lines. Okay, these are the few lines contained in this view here. Okay, maybe we can do. All right. So this is what it has, the small.txt. All right. Next is that this is the content of a small.txt file. Second is replacing something with something. Okay. It basically replaces anything from here with this. Okay. Replaces a pattern with another pattern. So here, what does it mean if you have gone through the regular expression session? Okay, regular expression session is available in session 1. Okay, session 1, the video as well as presentation is available in session 1, and it is important to learn regular expressions when you talk about the text search and text replacing. Okay, so make sure to learn regular expression. And this pattern here says the space or tab any number of time. So we are replacing space or tab by new line. Okay, replaces space many many spaces or tabs with new line. Okay, now next command is sort. What does sort do? Sort basically takes the input. Sort basically takes the input. Let's ignore this part for time being. Yeah. Sort takes the input and then sorted the data. Okay. It sorts the data. If you have ls and you pass the command to sort, it basically sorted the data. Zip came last and there you have this. All right. So sort basically sorts the data. Now, the argument here, you see the argument minus s. This is something very important. Even if you know Unix, you may not be knowing this part actually. A lot of people don't know this. So, sort has multiple features. One of the features is that it can sort using a fixed amount of memory. So, it says that sorts the data using only 1 GB of RAM. Okay. Now, the last one is here. Last one is unique. What does unique do? Unique command, unique minus C basically prints the frequencies in sorted data. So unique doesn't work on unsorted data. If you try to if you try to do unique on unsorted data, you will get wrong results. All right? You will not get correct results. So we talked about multiple commands starting from top. First one is first one is that prints the file onto the reads the file and gives the output, and then SED takes the input and replaces spaces with tab. It's like pressing Control F in your text editor, then replace something with something. Here we are replacing space with new line. Okay. And then whatever we got the result, we sort the data. And once we have sorted the data, we let unique find the frequencies of our data. Okay. So what is it we are doing? We are taking the input, we are converting into one word per line, then we are sorting it, then we are counting the unique words. All right. So this is one approach which is also quite common. All right. And this approach also does not suffer from memory limitations because takes care of sorting the data using a only fixed amount of memory. Okay. Again, it also does the similar thing. It basically splits data into 1 GB size each, then reads 1 GB data at a time, sorts it, then reads another 1 GB data and sorts it, and so on. It keeps on doing it until everything is finished. And once it has finished sorting the chunks of 1 GB, then it will merge the output of these sortings. Alright. So this way it can sort using only a fixed memory. So this is the approach we will talk about. So is this clear to everyone, this approach? Feel free to ask if there is a question. I would be more than happy to explain. All right. So Sabri says approach one is using language. Yes. Yes. Using programming, our usual programming. Approach two is using SQL commands, and approach three is using OS commands. That's correct, Sabrish. Now Surya's question is that why we should sort to know the count of words. All right. So here the unique command we are using works only on the sorted data. All right. I'll show you this. So imagine that. All right. So imagine that we have a file. Let me create a file. Hi, how are you? How are you? You are okay. Okay. So this is our file. Let's say I call it name as F. Okay. So cat F. Here you can see that these two U's are coming together while R's are on different lines. They are not sorted. So if you try to compute unique on this, the results are very awkward. So only U has been shown twice, while ideally R could have also been twice. So unique basically expects the data to be sorted. On the other hand, if you have sorted first, if you in the pipeline you put sorting as one of the elements, then you can see that R and U both are counted as true. Okay. Was that your question, Surya, or did I misread something? All right. Let me also try to copy the questions. Okay. So these are your questions. All right. This we have taken care of. And Sabri says, in which condition we pick up the approach out of the three? Yeah. Sabrishi's question is, out of the three, we pick up the approach. So confusion is amongst approach number two and approach number three. Approach number one is out because that suffers from the memory problems. Okay. So although using programmatically also you can do the same thing, what we are trying to do using Unix commands. Whatever we are trying to do using Unix commands, we can also do using programmatically. Okay. But right now, out of these three approaches, first one is out in case our data is really huge. If our data is very small, is smaller than what the amount of memory we can dedicate to it, then it's okay to go for this approach number one. While approach number two and approach number three is something which we need to discuss. Okay, Kalyan's further question is, what does it mean by S slash? So, which one are we doing? Yeah, S slash means because SED does multiple things. Here, this S means, this A here means substitute. Okay, it means substitute. Substitute, it says substitute this, this, and this. Okay, so if I have to write this in this manner, so it says, okay, substitute this with that, okay, and do it globally. Don't stop after substituting for the first time. Keep on doing it till the input ends. Okay. All right. Now the further question is, how is the intergroup chunks of the data sorting achieved? All right. All right. So probably you mean to say that if we sorted the input data, how would you merge it? Okay. How would you merge it? That's a problem, right? Because if you try to merge it just like that, the output, the resultant may not be sorted. Correct? Your question, if I understood Mohan correctly before I jump into it. All right, great. Let me try to show it with an example and then I'll leave you. So here the question is, how does the merging happen? Correct? All right, let me show you. Let's say that we broke down our inputs into three sets. Okay, set number one and set number two, and set number three. And right now, for our simplicity, we assume that we have only got numbers in the input. All right. So what does it mean by having only the numbers? So let's say that we have three rows of the data, or three data sets. Data set contains 1, 4, 6, 7, 10. All right. This is the first data set. Now second data set is 2, again 2, 5, 8, and say 50. And third data set, or maybe just 101 and 102. So each of them have been separately sorted. Individually, both of them are sorted. Let's take another case of the data. Let's say this one. So these data sets are sorted individually, but we want to merge these three data sets. So somebody gave us a problem, big problem. We split it into three parts: part number one, part number two, and part number three. And we sorted each of these parts individually, so that we have from left to right an increasing order. Okay, and remember that there could be hundreds of such inputs. So the way we generally solve this kind of problem is, we pick up the lowest value we pick up the lowest value out of this. So we pick up the head of the smallest value of each three data sets, pick up the smallest one out of these two, and smallest one here is 1 and 1. 1, okay, and 1. Correct? So we are left with these three, and this is our result. Now we pick up the next set and figure out what is the smallest out of it. Okay, and the smallest is these two values. Okay, and we put it here. Sorry. And again we do the same thing. We got another two here lined up. Out of these three values, what is the smallest? 2, right? We remove 2 from here. Now again we do this. We got, who is the smallest out of this? We got 3. And out of these two, what is the smallest? 4 is smallest. Then we have 5. We have 6 as smallest. then we have 7 and 8, we have 7, and then we compare again, we have 8, and then we have 10 as smallest, and then we have rest of it. All right. Now this way, this is the right way of merging the data. Now you would notice that at a time, we only had to compare the smallest of all these data sets. Okay. At a time, we only had to compare the smallest of all these data sets. Okay. And therefore it's fairly efficient one. But when the number of splits, number of chunks keep on growing, the problem becomes really difficult using this. So in those cases we used heap. Okay, so if you have time, basically we form the heap from the heads of each row, each of the chunk, and then use the heap for merging the data. Okay. So I hope that answers your question, Mohan. And I hope that's heap is another kind of a data structure which solves our problem. All right. So this is how the merging of mostly this merging of content happens when individual content is sorted. All right. Any doubts about merging right now? All right. So probably a description of heap would be a little too advanced and a little too off for this discussion. Probably you should have a look at the heap, okay, independently. We call it min heap, max heap, okay. A better thing to do would be look at how does min heap work, okay. We also call min heap or max heap. All right, we basically form a tree such that the smallest element is always at the top in case of min heap. All right, now any other questions right now? So this sounds like a lot of computer science, but do not worry. It is actually, I will try my best to make it more of a less of a computer science and more of a general discussion. Okay. But as a technology, we need to know how does sorting generally behaves and how can we convert our problems into sorting problems. Right? Moving on. Any questions? No. All right. Now, do you think there are problems with approach number 2 and approach number 3? Approach number 2 was we inserted our data into SQL and we let the SQL do the work for it. Approach number 3, we use Unix and let the Unix command sort the data for us. And then we computed the unique out of the sorted data. Now, do you see any problem with approach number 2 and approach number 3? Table size limit. Okay, okay, that's a good point. All right. So, Kalyan, the question is, do you see any problem with approach number two and approach number three? Sabrish says that we'll have to establish DB connection explicitly. All right, that's all right. Yeah, and splitting data into new line and word count takes more and more time if we have more data like 1 GB or more in approach 3. That's correct. That's correct. Yes. Does it not have the issue if the data becomes too big to handle by the single computer? That's correct. Yes. That's correct, Manish. All right. So any other points? In approach number three, we are opening multiple dataset at the same time and therefore may impose constraint. Yes. So, okay, let me try to say what I understood from your uh, point. So, when we create multiple files out of a single file, yeah, we are here talking about sorting. Sorting internally is breaking the data into, in approach number three, sorting internally is breaking the data into multiple files and then trying to merge it. And while merging, it is going to open all these multiple files at the same time and try to merge that. That's correct. So when you try to read multiple files from any file system, it suffers a lot. And the problem is not the file system or the software. Problem is the hardware. In hardware, in your hard disk, there is a header which has to move physically from one place to another. So when two people are trying to read the data from two different locations from the hard drive, it is going to hurt you really, really bad. The the header, the one which is reading the data from the hardware, has to keep jumping from one point to another point all the time. And since it's a physical device, it might suffer a damage. It will take more time. Okay, so that is why multiple dataset reading is an issue. Good point. Thank you, Mohan. Any other problem do you see? All right. So no other questions, no other points. Good. All right. If you have any questions, just let me know. So all right. So approach number two and approach number three. Although the RAM is no longer an issue, okay, and but the moment the data starts going beyond RAM, the following becomes bottleneck. And the things that become bottleneck is CPU, disk, disk speed, and disk space. Okay, so the way it happens in hard drive is there is a head which reads the data which is placed on the track in the hard, just like your cassette, and there are bundle of lots of records which like a roll. So head is placed on the hard drive from center towards the radially towards various points, and the disk rotates. Because of the rotation of the disk, it reads the data. Okay, so the faster the disk rotates, the faster it reads the data. So now, when we are trying to spill the data into multiple files, or we are trying to spill the data from the to the disk from the memory, meaning we are not putting things in the memory, we are just putting it back into the disk. So although we have removed the bottleneck from the memory, but now we are overutilizing the disk. So we have transferred our headache from RAM to the disk. And also, when there is too much work to do, sorting itself would take a lot of time and CPU might become the bottleneck. Alright? Although if you do the parallel things, the time taken by the CPU and time consumed by disk rotation can be done in parallel. While some data is being sorted, other data can be read. So those kind of parallelism you can do in case of approach in this, right? But still, either of them, CPU or the disk or both of these, could become the bottleneck for you. All right, now let's talk about a fourth approach. Okay, and the fourth approach is this: you have one machine on which your data is there. It's called launcher machine. And you bought two more machines, machine 1 and machine 2. So effectively you've got three machines. Machine 1, which is a launcher, could be a lower end machine like your laptop. Now this machine sends the data to machine 1. So this launcher is sending the data to machine 1 and machine 2, and both of these machines are merging the data. Both of these machines are sorting the data individually. I'm sorry. So launcher sends part 1 to machine 1, part 2 to machine 2. Machine 1 sorts the data, orders the data, and counts the frequencies and gives the result to the launcher back. And similarly, machine 2 also gives the frequency back to the launcher. Now the launcher machine merges the two data and gives the result. Sounds good? So whatever was the approach we used in approach number 231, we used those approaches in machine 1 and machine 2 to sort part of the data and let that data be transferred back to launcher and merged there and printed. Is this approach clear to you? So we bought three machines, launcher, machine 1 and machine 2. Launcher sends the data. uh, Launcher slice the data into two parts, part 1 and part 2. Part 1 goes to machine 1 and machine 1 does the computation, and machine 2 does the computation of the second part and gives the frequencies, and then launcher merges both of the data together. All right. And as we talked about, that merging the two data sets is comparatively an easier task if both data sets are sorted. Okay. So launcher does that little less heavy lifting while machine 1 and machine 2 do the heavy lifting. So do you see any problem with this approach? So is this approach clear first of all? If the approach is not clear, I will revise. I'll repeat it. Yeah. So Srinivas is saying the voice is breaking. Is it breaking for other people also? All right. So I think I missed one question. I'm so sorry. All right. Yeah. I think I missed one question from somebody. Yeah. Okay. Kalyan's question is, can you please explain the approach again? Yeah. Approach is you bought three computers. Computer one, computer two, computer three. All right. So out of these three computers, what you do is on first computer is your data. You divide the data into two parts, just maybe from the middle of the file. If your file is totally 3 GB size, you send 1.5 GB to machine 1, and rest of the file you send it to machine 2. And let these machine 1 and machine 2 utilize any of the approaches which we have described earlier, and then give you the frequencies of the word in the data, that too in a sorted order. In so the frequencies that these people, the both machine 1 and machine 2 return to you in the such that the words are ordered properly, ordered. Okay. Now launcher takes the two outputs from both machine 1 and machine 2, which is already sorted, and merges that result and sums up the counts of the words which are existing in both sides. Say for example, launcher sends sa re re to machine 1 and ga ga re to machine 2. Machine 1 returned the frequency of re as 2 and sa as 1. And since re is smaller than sa lexically as in a dictionary wise, so the resulting is this. Similarly, for the machine 2, we got the result as ga2 ray 1, and then launcher merges the two results and gives us this. Okay, so you can notice that ray has become 3. Okay, and the result is ordered ga, ray, and sa. All right, so is the approach clear, Kalyan, now? So yes, Basraj's question is, while merging the data, will the data set be copied to the launcher, or how does it happen? Yes, the data set will be copied back to the launcher. Excellent. Murli's question is, what if any of the machine goes down? Excellent. Excellent. Any other problem do you see here? So we also call this as external sort. Okay. So what's the problem with this approach? So first suggestion from Murli was, what if any of the machine go down? Anand is saying too much time transferring the data to and from machine 1 and machine 2 if we have large amounts of data. Very great. Excellent. So we have got 2 points. One is that what if any of the machine goes down? Other is that the transfer is happening. Transfer is taking too much time. Manish is saying launcher may be a bottleneck. Good, good. So we'll discuss these. Yes. Any of other points? Any other points? Just keep your answers coming, because yeah, do not worry about being wrong or right. Let the answers keep coming. So, do you see any problem with this approach? That is the question. This approach is called external sorting. All right. Yes. Network failure may be the problem. Yes. Okay. So, Vivek's point is, if we stick to the approach number one, that is maintaining a hash table, launcher still needs to have a map. Okay. So no, In launcher, we are not going to use the approach number one. While on machine one or machine two, we can use the approach number one, which is loading everything into the memory. And the way we will be merging is using the approach we just discussed. Okay, using a heap, and the launcher will be merging the sorted output in that manner. Basically, there will be two sorted data sets, and merging the two data sets is not a big deal here. So, Vivek, I want to understand your view. So Sabrish is saying it's a job tracker and task tracker approach. Yes, it seems like that, but there are those smaller nitty-gritties you will find that those are something which you need to discuss here. Okay. Okay. So, all right. I'm waiting for Lakshmikant sorry, Mohan to finish. All right. Yeah. Vivek is saying, I want to say that sorted map will ultimate be there on the launcher. Not necessarily. Not necessarily, because sorted map, if I understand correctly, is loaded into the memory, right? Not really, not really. You don't need to load everything into memory. As I was telling you that when I was showing you how to merge two data sets, all you need to load into the memory is the head element from both the data sets. Okay? The first element from both the data set. Okay? Rest can be in the disk. Manish's point is, if one of the machine is slow, your overall process will be slow. Yes. So the slowest out of the two, machine one and machine two, will decide how much how much time it will take for the overall process to finish. Okay. It will not be summation, but so slowest of the two machines, because they are working in parallel. Srinivas's question is, where will we maintain which chunks go to which machine? So yeah, that's another difficult question. So Srinivas's question is that how do we decide which chunk goes to machine 1 and which chunk goes to machine 2? So here, for the simplicity's sake, we'll say that first half of the file goes to machine 1 while second half goes to machine 2. Okay, it could be in the other manner also, that first line goes to machine 1, second line goes to machine 2, third line goes to machine 1, fourth line goes to machine 2, and so on. There could be many ways to do it. Okay, all right. So here we don't, if we have to just say that first half goes to machine 1 and second half goes to machine 2, we don't have to worry about maintaining this. All right. Good. So Anand's question is, what if the data is still greater than the RAM size of M1 and M2? Okay. In those cases, either you use approach number 3 and approach number 2, where the actual work was independent of the RAM. All right. What is the role of launcher? Just push the data to various machines. Yes. Push the data to various machines, and when it gets the result from machine 1 and machine 2, it merges the data using the same technique what we discussed when we did a merging of 3 data sets. All right. So Mohan's question is, machine 1 and machine 2 seem to be very efficient where launcher doesn't seem to be. We are taking the data to the code and not vice versa, and going against the very concept of big data processing. Are we assuming that merging doesn't have impact the overall performance? Brilliant, brilliant. So it's a very good point, and we will answer it over a period of time. All right. All right. Now we have Srinivas's question, and suppose we want to add more hardware for the computation in it. For the computation, it is the limitation. Correct. Correct. Yes. The network bandwidth will be another limiting factor. Great. As we are sending data across the wires. Great. So I think I have got all the answers which I was looking for. If I have to summarize your answers, first is time is being consumed in the transport of the data. Second, for each requirement, we will need to do a special purpose network oriented program. For each requirement, we'll have to do a special purpose. Now we are sorting the data. Tomorrow we'll be doing something else. Right now we were trying to do frequency analysis. At other time we would be doing something like some other problem solving. And for that we'll have to reprogram everything from bottom up. Okay. And that would require a lot of engineering every time we try to do something. All right. Because here a lot of time we are spending in transport of the data, and things like if one machine fails, what happens? So those kind of engineering is actually difficult to solve. Similarly, as some of you pointed out, that launcher is only single, right? What if launcher becomes the bottleneck? Okay, then again a lot of engineering is required to solve that problem. All right. So yes. So we saw these kind of problems in this framework, and that's when we realized that exactly these kind of problems are solved by MapReduce, and therefore we need to utilize MapReduce. So the problem the last so we talked about approach number 1, approach number 2, approach number 3, then approach number 4. And now the approach number 5 that probably solves it really well is MapReduce. Okay. And we go from approach number 2 to approach number 1 to approach number 5 as our data grows. Okay. If we have small data, our approach number 1, where everything loaded into memory, solves really, really fast. If the data grows a little bigger, then a database or the Unix command way solves the problem really well. But if the data grows little bigger, then we might have to utilize external sort. An external sort is not something which solves our problem really, because of the time is consumed in the transport of the data. And therefore, a paradigm like MapReduce solves a lot of problem, because in HDFS, we talked about HDFS. In HDFS, machine 1 and machine 2 already has data, so we don't have to transport the data. So we'll see that very quickly. So great. Now we understand. Now we understand that why do we require MapReduce? All right. So what exactly is MapReduce? MapReduce is a programming paradigm that helps us solve big data problems. Okay, so if you take a step back and look at it closely, MapReduce will be nothing more than a sorting engine, a big sorting engine which orders strings and gives us the result. Not only strings, it can sort the numbers also. All right. So MapReduce is a programming paradigm on top of Hadoop. It helps us solve really big data problems, specifically sorting intensive jobs, specifically those jobs which require a lot of sorting. Okay. So MapReduce runs on top of Yarn. Yarn we will discuss again. And so basically, you will have to code two functions. One is called mapper, other is called reducer. Okay. Basically, you will have to write two functions where one function will say that please sort my data using this key, and other function will say how to merge all the data using uh, based on a key. Okay. All right. So here we will go into the details again. Okay. We'll take our word count example again. It's not only Hadoop which supported the so it's not only the Hadoop which provides MapReduce, it's also other databases. When people realize the benefits of having MapReduce in systems like MongoDB, CouchDB, Cassandra, and Spark, everybody follows a similar pattern. It's more like a design software design paradigm. All right. And just like a for loop or like in SQL you have group by construct, we have MapReduce here. Okay. You can write mapper and reducer using Java, Shell, Python, or any other libraries. All right. So basically, your objective when we say that I'm working on my MapReduce, it means is you are trying to write mapper and reducer. Mapper is a function with, written by you which will decide what will be the key on the basis of which Hadoop will sort the data. And reducer will be another piece of code which will decide how to merge the data based on a particular key. As and this is the same key which were decided by mapper. All right. So let's have a look at one of the very simple problems. Imagine that we are trying to again solve our word frequency problem. Okay, we are trying to compute the word frequencies. So let's say our text file contain these four words only. So our mapper will decide that what do we how should we sort this data. And if you remember, everywhere we have been trying to sort our data using the word, right, based on the word. So our mapper here is saying that please convert this. Mapper is trying to convert this input into key value pairs where each key is individual word and value is something like 1. Okay, we could say x, y, or some other thing. Okay, so mapper's duty is to break down our text into key and value. All right, and then our reduce function, all it does is it sums up all the values, or it just counts. Okay, it just counts the all the values here for each key. Now sa re sa ga, that was our input data, became sa1, that is first key value, second key value re1, and sa1 and ga1. So this single line is broken down into four different key values, and this This dashed line is what is the duty of Hadoop. So Hadoop reads a file, gives it to map function gives out key value pairs, and Hadoop gathers these key value pairs and sorts them and groups all the values for each key. Okay. So if the key is duplicate, the values are brought together. As you can see, sa sa is duplicate, and therefore the 1 comma 1 has been brought together. All right, you can see that. And how to combine, what to do if there is a duplicate keys, that is the duty of your reduce function. And here all reduce is doing is sum up. Here, because ga has only come once, so the result is 1, but sa has come twice, and therefore array.sum results 2, which means it counted the frequency of sa as 2. Okay. So this is the most simple example of MapReduce. Okay, so basically you can see this as something like group by clause, where we in group by we decide on the basis of which our data should be grouped, and then there is another part which is called aggregation, where we decide how the group data need to be combined together. And that part is reducer, and the first part where we decide which on what basis we are sorting our data is called mapper. So Sabrish is saying while mapping it will allow to have duplicates. Of course, you can see that in the example. SA1 has come twice. Is it what you meant? Sa Sa has come twice, and that is the role of reducer to what to do with the duplicates. So all the values for the key are brought together. All right. So do not think in terms of Java map class. This mapper has nothing much to do with that. It's just a misnomer. So this mapper has nothing much to do with hash map or any other map. All right. So Manish's question is, will the map reduce solve only those problems which need aggregation? Not really. So and please note that as part of your map reduce paradigm, your program may not have reduced phase at all. You may say that I don't have any reduced phase. Let it be that way. Also, you can tell Hadoop that, hey, don't sort my data. This dashed line, you see, this dashed line is what Hadoop is doing for you. It's sorting the data given out by your map function. You can tell Hadoop that, hey, I don't want any map reduce, any sorting, so let my data be. Okay. So basically these are the various things you could do. So aggregation is not mandatory, as you can imagine. All right, did I answer your question, Manish? So Kalyan is saying that how the value of key is decided in the mapper. So it is up to your logic, your decision, on what basis you want to sort your data. Imagine that if you are spitting out the keys and values such that it's let's say for sa is the first letter S, okay, for Ray it's the second, or let's say your program in mapper just spits out, this gives out the second letter as key. Okay, I'm just talking a little uh, off the mark. So let's say your mapper, okay, the decision of what will be the key will is the duty of your mapper. Now imagine that your mapper is giving out key as second letter, okay, and value as the whole word. Okay, now what we have, a and SA, correct, we have e and ray, then we have a and sa, then again we have a and ga. Now you can see that this is the result of key value pair, result of your mapper in the form of key value pair. Okay, this will be taken by Hadoop, and what you will get is this: a, then you have sa, comma ga, then you have e, and you have ray. All right, is that clear, Kalyan? So now, correct. Then for each requirement, whenever you are faced with a challenge, you will have to create a map function. Okay, it will be up to you how do you plan that. Okay, so Sabrish's question is, other than alphanumerics, imagine that we have a video file as input containing 10 sessions. The requirement is to split the video session wise and send each session to a particular distribution list. Okay, do we use MapReduce here? How about working with media files like audio and video? That's correct. So whenever we say key, the only thing we are using text here just for the demonstration purposes. A key could be a binary data. Okay, a key could be a binary data. Similarly, value could be a binary data. In your case, we will take a similar example at a later point of time where you could break down things into always key value pairs to solve your problem. All right, and I like to understand this problem more. And all right, yeah. So these kind of problem can be solved very well. Imagine that you in the mapper, you are as part of your mapper. So I'm taking the example of Sabrishi's question. So in the mapper, what mapper does is here it writes down as the key called session number. All right, that's my key, and the value is the binary data. Okay, binary data of video. Okay, and so on. So we'll say session 1 and some binary data, and session 2 as some binary data, and so on. That is our reduce. Now in the reduce, that is our mapper. In the reducer, we will start send email for session. Okay, so reducer will get two things. One is session name here, which is the key, and the value, which is our video. Okay, and then it can send the okay, videos, not video, videos. All right, so you can do these kind of things as part of the mapper and reducer. So make sense to you, Manish? No? All right. Now, next question, good questions actually. Yeah, let me take it out, this one for a separate discussion. All right. So, next question is, so what characteristic one should see when they decide that MapReduce will be the way to go? I assume not all big data problems can be solved by MapReduce. That's correct. Yes. So anywhere where you see that the transport of the data will be the bottleneck, or you see that sorting is the intensive part of the game, and so those will be the places you will go for MapReduce. Also, the other way to look at what should go with the MapReduce will be to figure out what should not go with MapReduce. Okay, we'll discuss that part. What should not go with MapReduce. Okay, we'll talk about it at a later point of time. Okay, now, great. So I hope I have answered your questions. And any other questions? We'll talk about what should not go with the. So first answer was that generally sorting intensive plus transport intensive, okay, jobs. And second, it'll become clearer when we discuss what should not go as MapReduce. All right. Any other questions here? So here in this example, we talked about your data being only on the one machine. So it was easier and simpler. Now imagine that your data is existing on multiple machines. Node 1 containing one part of the data, node 2 containing second block of the data, and so on. Okay, this block, basically blocks are decided on a binary basis, but here we'll just assume that one piece of text is on one node, another piece of text is on another node, and if the line has been truncated in middle, the minor transport will happen to make it complete text on both sides. Or let me put it this way: out of the input files, if the input file contains a million lines, 500,000 line go to node 1, 500,000 line go to node 2. In case, because these are the blocks of data lying on HDFS already, the data is sliced anyway already, and first part of the data, first 500,000 goes to node 1, where whatever happened in the previous screen, the same thing happens. Okay, for each line our mapper converts it into key value pairs. Okay, so whole input given to map is converted into key value. Similarly here, and at both the places the sorting is happening, and the result from both the maps is combined together and given to your reduce function. Okay, so in this example, if you look at this example, here there was only one computer doing everything. Okay, it read the data, it ran your map function, and then gathered the result, then sorted it, then executed reduce and gave the result. All right, I think it's a break time, so let's take a break. We forgot the break. Yeah. And we will discuss this again. Right? So, all right. So let's start. Is everybody back? Should we start? All right. So, yeah. So, Pravita's point is that she was not able to access the session to recorded video last week. Yeah, I apologize for that. Because what has happened for some reason, it has happened for first time that this video has been after 1 hour 55 minutes. The video seems to be doesn't have any screen sharing. It only has the audio, and probably due to which YouTube did not accept our video. It kept rejecting. We even tried to split it. Still, it kept on rejecting, and because of which, after 3 4 days, YouTube has said that we are unable to process the video and they have removed the video. So we are trying to upload it, but again, it's fairly difficult to get it done. Okay. So most likely the video, the one which up to 1 hour 55 minutes will be available, while rest of the video I'm not sure will be made available. Okay, but till then you can actually use the second half. So let me try to upload only the I mean, let me try to put it on LMS, only the video up to 1 hour 55 minutes. Okay, so yeah, apologies for that. And okay, so here we have all right, so we are now getting back to our map reduce. All right, now the okay. So, all right. So, Sabrish's question is that we don't see much of a functionality in the reduce. Like here, all reduce did was summing up all the values for each key. Okay. So, in reduce, generally you it looks like that we don't have much of a functionality. Okay. But at lot of places reduce is required. It's like saying in the group by clause, we don't. Why don't we? The aggregate function does not play much role. All right. So it all depends on problem to problem. It just so happened that the kind of problem we are dealing with are something which which does not require the reduce. Okay. All right. Now, so is this diagram clear to everyone? So imagine instead of one file, we had two files loaded on two different machines, node 1 and node 2. Node 1 running the mapper and then giving the sorted results, key value pairs. Node 2 also running the mapper, giving the sorted results as key value pairs. And then merge happen of the two chunks, and then the merged data is passed through the reduce functions, and the result we get is like this. So let me go through the values. So imagine that on the node 1 section of the file is sa re saga, while on the second node we have sa re sa. After the map function, sa re saga is converted into this. Okay, and further the data is sorted here in the after the sorting on each node. This is the duty of Hadoop. Okay, the this step number 3 and step number 4 is the duty, actually, except for map function and reduce function, these three blocks, rest is the duty of Hadoop. Okay, so here basically first act of conversion of the input text into key value is the duty of your map, this one. And then the data got converted, that is the duty of Hadoop. And once data got converted, Hadoop grouped the data, okay, together. So as you can see, 3 and 3, both the sides, okay. So here you can see this. The result of from the first node is ga, re, sa, sa, and on the second one is re 1, sa 1, sa 1, and so on. Now this data will get merged together in this fourth step, and resulting will be ga 1. Re has come 1 and 2 twice, one this side and one this side, and Sa has come 4 times, twice on the right hand side, twice on the left hand side, and the resulting is we have this kind of output. And once we have generated this, our reduce function will be run against each key value pair, and you get this as the result. All right, Ga1, Ray2, and Sa4. Okay, and what does our reduce function do? Reduce function sums up all the values together. So 1, 2, 3, 4, and hence 4, 1 and 2, and hence 2, 1, and all right. So this way, MapReduce can run parallelly on multiple node. And also note that it's the same function. We did not make any changes from our side. It's the same function which is cloned on 2 nodes by Hadoop for us. All right. So it's the same function, whatever we did earlier. And this function does nothing but converts each input line into key value pairs. All right. So considering now Basura's question is that considering the sorting is taken care by respective nodes, who will do the merging? Any one of the node will do the merging for us. Okay, any one of the node, any one node which is free in the network will be picked up as by the job tracker and will run the merging. All right. Now here again, I'll go again. So let's look at this whole diagram with respect to Hadoop. So our file was huge, say 200 MB. It was broken down into 2 blocks of text. One block was the first one, second block was second one. In case because it is split exactly at 128 MB, so the separation of these 2 blocks may be that the last line is half into first block and half into second block. That could be the possibility. So that is transferred such that whole line is on one node. And so all right, so basically we have got 2 blocks. It's a 200 MB text, 2 blocks, block 1 on node 1, block 2 on node 2, and our map function, whatever map function we gave, is run against each line of the input, and this map function converts each line into key value pairs. All right, this map function converts each line into key value pairs, and then whatever key value pairs we get, we basically get sorted by each node 1 and node 2. And once that sorting is done, on the third node the merging will happen, and after merging, each key and all its value are passed to your reduce function. All right, and then the results are again stored in HDFs. Again, let me give another a rundown. So when we ask Hadoop that, hey, can you execute my map reduce, so we do few things. First, again, let me open another text file. All right. So we tell Hadoop, the input to Hadoop is, or input to MapReduce is, here is my file, my input file, which is uploaded already on HDFS. Here is my file, which is of 200 MB. Okay. And then the next is my map function. So let me just write the map function prototype for you. So this is your map function. You will write a map function like this, basically, which emits key and value. It emits key and value for blah blah blah. For some logic you have, it emits key value. All right. Here in our example case, what it will do is for each word in line, it is going to emit word and 1. Okay, this is a pseudocode, right? And then the next output I would, so one is my input file. I'm telling MapReduce that here is my input file, here is my map function, and here is my reduce function. This is my reduce function. Okay, this is my reduce function. And what does this reduce function do? It basically gets key and array of values, array of values, okay, and it returns some aggregation of array of values. So this is how your reduce code would look like. All right. So you have map function, you have a map function, and you have a reduce function. Sounds good? It's a pseudocode. Don't try to think that it's a programming language. Okay. I'm trying to keep it in pseudocode because that would be very simpler to understand. Okay. And next is output folder location. So you tell MapReduce that here is my HDFS file, here is my map function, here is my reduce function, and this is where you got to store the result. All right. And what will it do with it? It will find out where all the blocks are located in the network. And once it has found the blocks, say node 1 and node 2, and this block contains this text and this block contains this text, it will run your map function, which will basically convert the input into each line into key value, and that data is gathered by Hadoop, sorted, and then merged together. After sorting them, it is merged together. And then, of course, from sorting to grouping should not be much of a hassle, because grouping a sorted data is a very straightforward process. Okay, because you also can see, right? So if you have to group this data, it will be very straightforward. All right, it will be ga1, ray1, and sa1 comma 1. You just go from top to bottom, identifying the moment you hit a different key, you can say that we our grouping of the previous key has finished. All right. So everybody okay till here, or should I? Yeah, can I move forward now? Correct. So Srinivas's point is key means word name in reducer function. So whatever you decided here, whatever key is here, the same one will be here. That's correct. So Kalyan's question is, always block and map reducer will have one-to-one block and map reducer will have one-to-one mapping, or one block can be sent to multiple rooms. Okay, so that's a very good point. So Kalyan's question is, here in this diagram we see node 1 and node 2. We have block 1 and block 2. So his question is, will it always be one-to-one mapping, that one block, one mapper will be run against one block, or can one mapper run against multiple blocks, meaning multiple blocks are being gathered from multiple nodes and being run, being consumed at node 1. So generally, although this is fairly customizable and controllable, but still, generally the general strategy is you keep one block and one map phase. Okay, to avoid the transmission of too much of data from here to there. Alright, so here our map was taken to multiple nodes and got executed. This is the classic example of how do we take computing to the data rather than carrying the data to the computing. Alright, uh, alright. Any questions on this screen? Where reduce will execute? Reduce will execute on any node which is free, not necessarily on node 1 or node 2. Most likely it will be on node 3 or some other node. Right, this merging will happen, and the execution of reduce might happen in the network. Now you may say that there is a network transmission here. I agree that the network transmission is there. If you have this merge running on some other node, then the data will get transferred from node 1 to node 2, node 1 and node 2 to this node 3. And yes, there will be a network data transfer. That I agree. Yeah. Anand, is that clear? All right. All right. So the way it happened was, let me just go through it quickly from end to end. You uploaded your file onto HDFS, which means it got broken down into blocks, block 1, block 2. Okay. Here in this case, we had 200 MB file. First block is 128 MB, and second block is how much? Can somebody help me out quickly? 72 MB. All right. Now, now we wrote the, and then it has been broken down into into blocks. Now it was stored, we were happy, and then we had to do the word count suddenly on this file which we stored on the HDFS. So job tracker we told job tracker, hey, I want to do my map reduce. Here is my map function, here is my reduce function in this form. Here's my map function, here's my reduce function, and this is the file which I want to churn in my mapper, and this is the output folder where our results of reducer will go. Now this job tracker finds out which all node contains this block, and also finds out which all nodes are free to execute the work. And these nodes which are free to execute the work, it picks up out of these nodes, these free nodes, it picks up the one which is the closest to the block. Or you can say it's on the same node. Okay, so generally, the way job tracker will pick the node 1 or node 2, will be based on how close are they to the data. Once it has figured out that okay, we are lucky and we are having node 1 and node 2, which are on the same, which are same as the node that contain our HDFS block, and then it will ask both of them to do the work. So each task tracker will take your map function, will execute this map function again line by line against the file, and then your map function will give out key value pairs on each node will take the key value pairs from your map function and basically gather all the key value pairs from on that node, then sort those key value pairs, and then once it has finished sorting it will send it to third node where the data will be combined from all these nodes running the mapper. The data will be combined together, and then once it has been combined, merged, and sorted, for each key values, for each key, the reducer will be executed against key and the values, which means the reducer will get two things. One is key and other is array of values. Okay. So sorting and merging are predefined, or do we have to need? No, we don't have to write a code. All we can tell Hadoop is turn off or turn on the sorting. In case we don't have any reduce phase, we can tell don't sort my data. Whatever map is doing, take it directly to the HDFS. Save the result directly into HDFS into different files. All right. So Manish's question is, so how does job tracker decide where to execute reducer task? Are there any factors that help the task tracker to execute on a particular node or no? It doesn't do it that way. It tries to figure out the node which is closest to the nodes of mappers. Okay? The nodes which are closest to the node which contain the map. Okay, if there is only one rack is an almirah in which you put your computers in the data center. If there is one rack containing both the node 1 and node 2, then it will try to execute reducer on the same rack on some other computer. It tries its best to execute the reducer closest to the mappers. Yeah, we'll give that demo, no worries. All right, let me just have a look at more questions. All right, this is answered. Can there be more than one reducer at the final master? Good. We'll show this in the next diagram. All right. So his question is with respect to multiple reducers. When the map reduce or executes on a node other than having the data is copied to that node. Yes, the data is copied to that node. If yes, and is the data removed from that node after the operation or left there? The data is immediately removed after your map reduce gets finished. All right. Next question is, in that case, yeah. So in that case, how Hadoop knows what key field to sort on? That's exactly the role of your mapper. That's exactly when we say that your mapper is going. So Kalyan's question is, if the duty of sorting and merging the data is of Hadoop, on what basis does Hadoop sorts the data? So that's exactly the role of mapper. Mapper, whatever key you define, Hadoop will sort the data based on that key and merge the data just based on that key. All right. Now, next is please give a demo. Yes, we'll give a demo. Is there some kind of predictive algorithm like All right. Is there some kind of predictive algorithm, like if the data node is not free, instead of running map on another node, does it have to wait? Does it try to wait for some time, or to see if the data gets free, or instead of that, immediately moving the data? So basically, it tries to whatever nodes are free, it tries to execute it then and there. In case no node is free, then it waits. So that algorithm, basically resource manage, these all are part of management. And these algorithms are improving every day, Vivek. And those are the questions probably, Hadoop keeps on answering every now and then by trying to optimize various levels. Okay. In all these, where is the data replication happening? So data replication is happening on, as usual, on HDFS. And this block one, when we talk about, okay, this block one, when we talk about on node one, it could be the actual data or any of the replicas. Okay. Map and reduce functions is stored in the memory or file or both. Do you mean to say the output of map is stored in the memory? Is that what you mean to say? Yeah. So the output of mappers as well as reducer both go into the disk, while intermittently the result of mapper is gathered into the memory, and once that is done, it is spilled over or saved to the disk. All right. Okay, Vivek. So which question do you mean to say? The first one, this one? Can the reducer be? Yeah. So now we are going to discuss that, Vivek. All right. No worries. All right. So the next screen is about multiple reducers. Okay. So here, so Sabrishi's question is Hadoop a framework, or do we have IDE to develop? So there is no separate IDE for Hadoop. Eclipse will do good, or any of your programming language. If you are working on Python, your Python dev or IDLE and whatever will be good. You can develop on any of the IDs. Once you have done that, you can upload your program onto Hadoop cluster and get it executed there. Okay. Your development workflow will continue in the usual fashion. It's just the deployment will happen onto Hadoop. All right. Now let's have a look at what happens in case we realize that, hey, the reduce function is taking too much of time. Say we are computing a complex thing over all the values for a key. Say we are doing the root mean square value. Say we are doing root mean square value. Root mean square value is we try not I mean we try to compute a square plus b square divide and so on, divide by n, and then we again do the square root of it. Now in these cases, when the complexity of reduce increases, the machine on which the reduce was running might become bottleneck because it was singular. Now, we can tell Hadoop that can you run my reducer twice, while number of mappers was decided by Hadoop based on how many blocks your file has. Number of reducer is something you control. You tell Hadoop that, hey, can you run my reducer on 10 nodes or 1 node or 15 nodes or 100 nodes? All right. That way, what will happen is after the node 1, node 2, and all of these things have finished preparing the key value pairs, these keys are redistributed onto multiple reduced nodes. And and just that, while redistribution, Hadoop guarantees that one key does not go onto multiple nodes. All the values for a particular value go onto a single node, no matter how many reducers are there. So that is something, a promise from the Hadoop side. All right. As you can see that here, here you can see that. So after the third, you see here, the data got merged, say ga, re, sa, sa. So after the data got merged, ga, re went on to first reducer, while sa went to the second reducer. So it never did not happen that one key went to the other nodes. No. One key and all its values are always passed through the single reducer, no matter what. That's a promise of Hadoop. Okay. So some of the keys go to one reducer, some of the key would go to another reducer, and so on. If you have 10 reducer, there will be 10 different buckets, and in 10 different buckets, the 10 different reducers will be executed. But no matter how many reducers are there, one key does not go to multiple nodes. It would never happen that for one key, say key 1, and containing value 1, value 2, value 3, value 4, one reducer gets key 1 value 1, while another reducer gets key 1 value 2, and so on. Always you will get all the values for this key. So key 1, value 2, value 3, they all go to the same reducer, no matter what. Okay, that's a guarantee from Hadoop side. Okay, so Kalyan's question is that the code in containing our MapReduce, it could be, no, it would be, it may be .exe, but not really. It may be your jar script, jar file. It could be Python script. It could be shell script. It could be anything. And his further question is that, does it have to be loaded on all nodes, or does it have to be, can we just launch it from one place? So yes, we can launch it from one place. Hadoop will copy this on all the nodes and execute it all the nodes parallelly, right? It doesn't have to be available on the same node. Perfect. Moving on. Now, this is how you can think of MapReduce function when you think of breaking down. So if you remember, we said select word, comma, count star from a table group by word. So here, the second phase where we are saying, this is my table, and this is the basis of my grouping, is something that's a decision taken by map in our case. And the moment we say count star is equivalent to the reduce function. All right. So aggregation is equivalent to the reduce function, the while selection of the word is basically equivalent of the map function. Is this example clear? Is this clear to you? How is it analogous to group by? All right. So we will discuss four problems, and before that, I would like to give one more example. Okay, because it should not sound as if I okay. So imagine that. Okay, let me answer Srinivas's question. Suppose we have multiple map and reducer. One map and reducer output goes to input to another map and reducer. How to configure these things by programming a configuration? So okay, so the question is that say you have map 1, reduce 1. This is one piece of code. Another one, map 2, reduce 2. This is another. So first, the input is coming from HDFS and going back to HDFS. Correct? That means you could chain them together like this. Okay? Because while executing map 2 and reduce 2, you can execute this. And yeah, and you would wait for map 1 and reduce 1 to finish, and then you will execute map 2 and reduce 2. Only then you will launch it. The easier way of doing all of this is using Uzi. Uzi will do these kind of things for you. Alright? We'll discuss Uzi at a later point of time. Good, good. Now let's take another example. Let's say there is a temperature table, okay? Temperature data of world. Okay, and how does this data look like? This data looks like the sensor ID, city name, and coordinates, and then zip code, and then temperature. Okay, this is the data we have. Okay, each line is defined in this way, say one, and okay, and then city name. Okay, city name, say Bangalore, and coordinates is something of this sort, and temperature was 10, and so on. For all the data we have is okay. All right, this is the temperature data you have. Is it clear to everyone? All right, so imagine that you have got the temperature data across the globe, and what you need to do is find average temperature for each zip code. Okay, what will be the mapper and what will be the reducer? Yeah, anyone? Inside our mapper, what will be the key and what will be the value you will do? And inside the reducer, what will you do? Okay, so Basraj says that mapper will be giving zip code against zip code as the key will be zip code, and value will be temperature. Anybody else? Anand also says the same thing. Okay, anybody else? Yeah. Good, good, good. All right. Now in the reducer, in the reducer, what we will be do will we do? Reducer will basically returns average of all the values. Okay, because reducer will always be run, the function will be executed per key basis, so at a time it will only get all the values for the key. So this will give us, this kind of a code will give us the average temperature on each zip code. All right. Great, great. All right, so that was one example. Now I have four questions to you. First one is, instead of doing frequency of words, what if we had to do frequency of letters? Okay, for a humongous data, we are trying to do frequency of letters. We are trying to compute how many times A came into play, B came, and C and D, and so on. That's the role of our frequency computation, this problem. Now, do you require map reduce in such case? And frequency of letters is a very frequent phenomena that is done in cryptography, as well as detecting the language based on frequency of characters. All right. Now, my question to you is, do you need map reduce in this? So think about these four problems which I'm giving you. We will discuss these four problems again tomorrow. Now, next question is, find anagrams in the Hughes text. An anagram is basically a rearrangement of letters in a word. Okay. For example, for example, in this sentence, cat, act, and tech, they are the rearrangement of A, C, and T. Correct? And hence, these are the anagrams in this text. So if you are provided by Hughes text, and you have to find anagrams, what are the anagrams in this Hughes text? What How will you form your mapper, and what will be in the reducer? Okay, or in another words, what is going to be inside mapper such that all anagrams come together? What should be the key in your mapper such that the key should be same for all the words which are anagrams to each other? So Srinivas's question is, both mapper and reducer are required? Not really. Not really. You can have without a reducer also. You can tell Hadoop that, hey, I don't want to give reducer and I don't even want sorting. Okay. So those kind of options are there. So is the question number two clear to all? Should I explain the question number three? Oh. So Srinivas is probably trying to answer question number one. So let's have answer tomorrow. Okay. And I'll tell you how to a way to answer these questions. Okay. So you can go to the browser. Okay. Go to the browser. Go to knowbigdata.com and go to my courses there. All right. Okay. I'll explain to you this question number two and three and four quickly. So under my courses, you will see 2nd May. Under 2nd May, session number three, Okay, session number 3. And what is wrong with this? Yeah. In session number 2 itself, you will see map reduce subjective questions. Yeah, this one, Sabrish. Okay, you mean to say presentation? Let me see. This one? Yeah, it's opening for me. All right. Maybe your company has restricted the Google Docs. Okay. So here you click on the map reduce subjective questions, and you will see these. Here you have to answer each one. Okay. So one by one you have to answer. I don't require code in this case. You just have to write theoretical explanation. And you also okay. So even if you here you have to answer in explaining that why do you require map and reduce, and also if so, if you and you have to write map reduce a logic what would go into the map and reduce. Okay. Now the second question here is, you can see, find anagrams in Hugh's text. An anagram is basically different rearrangement of letters of a word. Okay. For example, cat, tact, and act, all three of them has the same letters. Okay. So you will have to bring the output such that, so, or let me just take it further. If our text was this, in this era, people are uh, people are clever. All right. Okay. So here you can see that cat, act, and tack, these three words are anagrams, and R and era are anagrams. So if you are given a humongous text of few GB, what will be your map and what will be your reduce in order to find out the anagrams of each other? Is it clear now, Kalyan? Sorry, era. Okay. The next question is, there is a file that contains the DNA sequences of people. Find the people who have exactly same DNA. And the file contains user one and and the DNA and so on. So what would be the key and the value? All right. This must be clear to everyone, right? So for example, user one and user four, ACGT, are the people who have the same DNA, and user 3 and user 5, ACG, while user 2, which is TGCA, do not have anybody else sharing the same DNA. All right. So if you have to do this kind of thing, what will you do? Okay. What will be the key and value in case of mapper, and what will be the logic inside reducer? Okay. So solve it Here, write your answer here, Baswaraj, in this box, and then next. All right. Right now, I'm just writing leave blank. All right. Now the next question is little more tricky. It's also the anagrams question was also little tricky. You have to think about anagrams question a little harder. Now in this question, the problem is you have to, some research said that if people have either identical DNA or if they have mirror image of DNA, that means they belong to the same family, and therefore you have to bring all the people together who either have exact same DNA or have mirror image of the DNA, either exact same DNA or the mirror image of the DNA. All right. So that is your role to find out such people. Bring together these people who belong to the same family. So question number 4 is clear to you. All right. So question number 5 is little trickier. So in this, there is this country where the democracy is very unusual. In this democracy, the people whose worth is more, their votes are counted. Their votes matter more. The rich people's vote matter more as compared to the poor people in this democracy. Okay? In this unusual democracy, everyone is not equal. The vote count is a function of worth of the voter. Though everyone is voting for many people or maybe each other, so lots of people are voting for lots of people. It's not that there are only few people who are being elected. There are many people who are being voted by each other. Okay. Now, for example, in this diagram, list 1 contains who voted for who, while list 2 contains what is the person's worth. Okay. And what do we look for? So in list 1, A voted for C, B voted for C. That means the vote count of C will be A plus B. And the worth of A is 5, B is 1, and therefore the vote count of C is 6, 5 plus 1. Similarly, C voted for F, and C's value is 11, and therefore the value of the total value accumulated by F by virtue of being voted by C is 11, while nobody voted for A and B, their value is 0. Now the question to you is, how do you, given that both list 1 and list 2 both have millions of records, okay, maybe 10 million record each, how would you compute this result? How would you compute who won, or how would you compute the final vote count? Is the problem statement clear to everyone? So this problem is little tricky, okay, and it requires these few knowledge that when we give MapReduce, we can tell that these are the multiple files that need to be concatenated together before being given to my MapReduce. Okay, so those files, you can give multiple input files to your MapReduce program, and these all input files will be combined together, concatenated together. All right. Second is you can use multiple MapReduce, and you can say the output, because every MapReduce phase will save the output to HDFS, and also every MapReduce will read the output to from HDFS. Therefore, chaining these MapReduces are not very difficult. Okay. So is the question okay? Should I move ahead? All right. If there is there any doubt in any of the for 5 questions? And also, while you are at it, you can click on user account and then see my results. Okay, it'll show you the results of your previous attempts. You can keep on attempting the quiz and subjective questions as many as times you want. Okay, and then you can see your answers. All right, are you with me? Good, good. So please finish this quiz, these subjective questions, and then we'll discuss it in detail. All right, now moving ahead. All right, so yeah, we are running one session behind, so no worries. Okay, I'll restructure these presentation accordingly. All right, so let's start with something called a Hadoop streaming job, and then we will tomorrow we will discuss in detail the answers to the previous questions, and then we will go into further details. All right, now there is something called Hadoop streaming job. That is probably the easiest way for executing your mapper and reducer. It can take, it's a library which makes it possible to use any binary, any scripting language, or any program which can take input and give output. Okay, so Hadoop streaming can utilize any such binary program or script to to run as mapper and reducer. All right, so for example, this is one such program. Okay, so as we discussed earlier, so we said that SED replaces space with new line, while unique basically finds unique values, basically counts of each word. All right, and so on. So this is how it looks like. All right, and the way you run it is quite simple and straightforward. So let me first bring it to a single line. I'm bringing it to the single line. Okay, because it doesn't run that way. Or if you have to run it in like this, you could have said this kind of a slash. Those who are coming from C background, they will be able to identify quickly. All right, now what does it do? It basically executes this program. We tell Hadoop, please execute my program. Instead of saying fs, we are saying jar here. Okay, instead of saying fs, we are saying jar, and here we are telling it that this is my program which contains my MapReduce code. This is the program that contains MapReduce code, and in this case it's just a streaming job. And what does a streaming job do is it considers any binary we provide as mapper and reducer. Okay, so this is a utility class which basically make it possible. This Hadoop streaming.jar is the one which makes it possible to run any command as the mapper and reducer. All right, now here we are saying Hadoop jar and streaming jar, and then we are providing our input folder, our output folder, and the command that should be used as mapper and the command that should be used as reducer. All right, so let's just execute it. Okay, so before that, before execution, I'll have to SSH. Interesting. So I'll say SSH hadoop1.nobigdata.com, and before that I'll have to put student. So here I've pasted the command, I'm running it. Alright. So it must give an error. It says that output folder already exists. Okay. So let's change output to say 2 May. Okay. Okay. So that will get executed. It's getting executed. Now in the meantime, let's get a look at what's going on. Okay. So it will execute this as mapper, this as reducer. This will do, what will this do? This will give out the one word per line, and that is the mapper. Okay, which means that there is no value is null, but you here we do a count on each value. All right, as you can see that when a job is executed, few things to note. First, if the output folder already exists, it gives an error. Second, all these output folders and input folder both are in HDFS. Third, when it starts, it gives it a URL to track. Okay, any batch process when they try to whenever there's a batch process, it basically tells you that don't wait for me, I might get delayed. Here is the way to monitor whether your work is done or not. Okay, now this is the interface where you can see what's going on with your mapper and reducer. It says that both have become successful. All right. And once it is done, it prints out all the statistics with respect to how much data was read and what actually happened. Okay. And the output is stored in this folder. Okay. So you can say Hadoop fs minus cat, or let's say minus tail, and sorry, we'll have to say first ls. Let's see what's there in that folder. So you can see that. So this folder contains two files. One was underscore success, which has nothing but 0 bytes. Then there is another file which contains the data. Okay. So this is the output of our MapReduce. All right. This is the output of MapReduce. Let's understand what actually happened here. All right. So here the mapper is our sed command, which converted each line into one word per line, while reducer did is just counted how many times a word has occurred. Okay. So let's have a look at what actually goes on. So few things to note here. The biggest difference between normal MapReduce and streaming is that input to your reducer is not grouped, it is just sorted. Okay, as you can see, instead of saying sa square bracket 1 comma 1, it's just sa and sa. Okay, so the output of mapper need to be in key value format, and these key value need to be separated by a tab. Okay, so these are the few things which Hadoop streaming enforces. Hadoop streaming says I can execute any program as mapper and any program as reducer as long as your mapper is giving out key value pairs separated by tab. If I do not find a tab in the line, then whole line will become the key and the value will be null. That's what Hadoop streaming says to the developers. Okay. Now in this case, since we have only one word per line, the value is null while key is the word. Alright. Once that has been done, it basically converted sa re saga into sa re saga as something, and that's the key. There is no value. Value is null. And the results of sorting are not grouped and they are just given to unique minus C. And unique minus C, what does it do? It counts the unique occurrence of each word in the input as long as the input is sorted. Does it make sense? How did it work? So yes, mostly the streaming work only with the text file. Okay. To make it work with the binary file, you need to have the you need to have the program which can take the binary data as input. Okay. For example, if you have used a command called tar, or a command called zip in Unix, they all accept binary data on the standard input. Okay. So the input can be binary as well. And as we said, that key value need to be separated by tab. If there is no tab, the value will be null. If there are multiple tabs, the first tab, the value just the string just before the first tab will be considered key, and rest of the uh, part of the sentence or part of the line goes to the value, which means value will contain tab in case there are multiple tabs. All right, is it clear? So before we move on to a Java kind of a MapReduce, the full-fledged MapReduce, we are trying to explain how does MapReduce work using standard programs. And this is very important to know because 90% of the time you will be happy with the streaming job. My first introduction happened via streaming jobs. All right. So if you are from say Python background, there are projects like PyDoop, but those are heavily underdeveloped. Okay. So it does not make sense to use those projects right now. But you can use a Python with the streaming job and it will just work perfectly fine. So alright, so streaming job is clear to everyone. Similarly in streaming job, if there are multiple reducers, this will happen. But again, at any level, the all the keys will remain together. Like Sa has gone to the same node, and Guy and Ray have gone to different nodes. Okay. When it comes to multiple reducers, reducer always have same key on the same node. All right. So is this clear to everyone? No, if it's not clear, then we can discuss it again. There is no harm in discussing it again. All right. All right. Then now what happens is in this case we ran our SED, which converted each line into that, and then we did unique minus C. This is the result we got. Now you can have a look at it. It is very dirty. you can see that it's fairly dirty, right? Jinc comma, jinc dot, jinc semicolon, and all of that have come together. Ideally, we should be cleaning this data so that there are no special characters. And also, the lowercase, uppercase, those kind of problems need to be solved. All right. So that's the next step. So what we do is now instead of having a single command, we create our file. We create our file mymapper.py and so on, and then we run those things. Okay. And we also tell Hadoop that these are my program. Please take it and deploy it everywhere. Okay, when you say minus files, it will take you these program of yours and distribute it wherever it's running those programs. Okay, as somebody was asking in the session that what happens if my exe is not installed. So this is the way to go ahead. So in case your map reducer is not only just a single command, your map reducer is the program which you developed, and there is, you don't know whether your program is installed on the cluster or not. Okay, is it installed on all the nodes or not? In all those cases, you use an option called files. All right, so we'll discuss this example tomorrow. Till then, try to solve all these 5 questions and have a good day. Please submit it in the subjective one, and we will discuss it tomorrow. All right. All right. Thank you, Basraj. We will see you tomorrow, and have a great day. All right. Have a good day. Bye bye. Stay connected. And Pravita, I think I have replied to your question in the support. Probably I need to check it again. All right. So I may not reply in the full-fledged manner. I may reply very quickly, but that should be sufficient mostly. All right. So Kalyan, I'll try to start the upload as soon as this session finishes. It might take like 3 hours to make it available. Mostly the YouTube takes a lot of time to process it. Okay, we need to figure out a better solution. Okay. All right, Kalyan, then have a good day. Bye Anand, bye Basraj, bye Kalyan, bye Lakshmikant, bye Manish, bye Mohan, bye Murli, bye Pravita, bye Sabrish, bye Srinivas, bye Surya, and bye Vivek. All right.